Screencast is going to follow the electron transport chain oxidative phosphorylation screencast from before, and it's just a supplemental one because I want to talk about the fate of FADH2 and the fate of the NADH from glycolysis. So the FADH2 and the NADH from glycolysis, which I'll just start calling NADH sub G. This isn't really from any other textbook. This is just my notation here. So these FADH2 and NADH from glycolysis have a less free energy, lower G, than the NADHs from the Krebs cycle. Right? So NADH KC. So consequently, since they have lower free energy, why, that's a whole other question, but just that they do, it has consequences for then how many protons they can pump. So here's the NADH from, all right, now school's over. So there's the NADH from the Krebs cycle. And now I want to look at the FADH2 that's produced here. So you notice that the left part of this graphic is grayed out. So this is not happening. So here's FADH2. So when FADH2 is going to be oxidized in oxidative phosphorylation, but it enters the electron transport chain at a lower free energy because it itself has a lower free energy. So as I oxidize FADH2 to FAD, electrons get transported, right? And if I'm moving electrons, then I'm moving protons, right? If I'm moving electrons down an energy gradient, reducing oxygen here to water, I can pump protons, right? So this pumps 2 protons and that pumps 2 protons. So consequently, I'm still making a gradient here, realize, right? Like there's still a proton gradient that's being made, and this is happening in addition to this, right, part as well. So I've got this oxidative phosphorylation thing happening. I have this happening at the same time at a different electron transport chain somewhere else in the membrane. Right? This is why the folding of this membrane is important, right? So this membrane is folded. I have lots and lots of electron transport chains all throughout this membrane. And I have, you know, if one of them right here is oxidizing the NADH from the Krebs cycle, then maybe this one over here is busy oxidizing the FADH2, and so on and so forth. So I can pump these protons here into the intermembrane space, creating that gradient, and then utilize that gradient over here in chemiosmosis. So the accounting, though, is just a little bit different. So for every one FADH2, this ends up only pumping 4 protons. And then that, I don't know what this is all about, is 4 protons. And then this translates directly into 2 ATP molecules, right? Because this 2 is 1 ATP, and this 2 chemiosmosing is another ATP. Right? So there's FADH2. And here's the NADH from glycolysis. Behaves much like the FADH2 from the Krebs cycle. So this is NADH sub G. This NADH from the from glycolysis will be oxidized. Electrons donated to the cytochrome, and electrons move. And as electrons move, you pump protons. Right? You create a proton gradient up here. You then utilize that proton gradient in chemiosmosis over here. Right? So this NADH from glycolysis. So for every 1 NADH from glycolysis, this is going to be 4 protons pumped, which is going to be 2 ATP molecules. Right? So we'll do the accounting in class and add this all up and see how we can get ultimately all that ATP made from the electron transport chain. But there's a couple little supplements. Here is the free energy gradient we saw in the other slide. So now we're not dealing with this NADH here. We're dealing with the FADH2, and you see that it's at a lower free energy. This is the NADH from the Krebs cycle, right? But I was just talking about this FADH2 here, and then also at that same energy level would be the NADH from glycolysis. Right? And again, so that's not utilizing this cytochrome right here. We're picking up the story right here. So as the electrons move this way, right, they're falling, they're cascading less, so they're then going to pump fewer protons. Right? Fewer protons pumped, fewer chemiosmosis actions happening, fewer ATP being made. So just a quick little supplement, and hope that is helpful, and I will see you in class.